Hello, my name is Robert and welcome to my series on how to implement some machine learning algorithms in LabView. This will mostly be my homework for the virtual instrumentation laboratory for my university, and since I will need to record myself while I'm doing my homework, I've decided to also post it on YouTube, since maybe sometime in the future somebody will need to know how to do this too. I will implement some easier algorithms, some fundamental stuff such as Hebbian Network. I will also be doing some comparisons using Python node from LabView, because I want to see if I will call a Python implementation of the same networks, if it will take longer or if it takes shorter time to complete. And I will also be using some parallel programming, since I don't want to have some bottlenecks regarding running multiple networks in the same time. So let's start by reading our dataset. For this I'm going to use CSV files, since it's going to be easier to read our data and to play with it than to hardcode it into our program. For this I'm going to use the read delimited spreadsheet block. This needs the path to our dataset. Here you're going to need to be careful, since this block needs the absolute path, not the relative one. We are also going to create a new indicator to see if our dataset has been read correctly. This is going to be a classic CSV file, so our delimiter is going to be a comma, and our data is going to be of type integer. Now let's see if this works. And how you can see, our data has been read correctly. Here, this is what I was talking about. You need to give the whole path, not the relative one, because if you are going to give the relative path, you're going to get an error. Now let's create a sub VI. So since we are going to be using this more often, and for this let's select all our blocks, edit, and create a sub VI. If I'm going to find it. Now our sub VI has been created. You can double click on it to see it more clearly. Now let's see. So basically what this means. This is going to take as input our file path, and this is going to give us output our data. Let's change our icon, so it's going to be something more to know better what is this. Let's see if I'm going to find this. So CSV, so I'm going to know that this is our CSV file, but let's this, not this. I'm going to try to select the text if it's going to work like this. So now you see my file is here is a small CSV, so you are going to know that this is our CSV block. Our activation function for this network is going to be a signum function of parameter net being the cross product between one row and the waitlist. The good thing is that all of these are already implemented in LabView, so we are going to use that product that is from linear algebra. This takes as parameters two vectors. Basically it takes two lists. Now to take two lists, because here we are having two matrices, because this is a list of lists basically, and this is a list of lists too. So because of that, you are going to be using index array And to extract only the wait list, we are going to create we are going to take only the first row from the because basically how we implemented our CSV read sub vi is going to give us a matrix, even if it's basically one line like this, and this is going to tell us this is going to give us only the wait list. And now to get a data set, we are going to use the same method. We are going to be using an index array. We are going to wire this up to our data set, and this is this is an index for our data set. For this, I'm going to create a constant. I'm going to move this a little bit farther because we are going to create a sub vi after. And after, let's create now an indicator to see if all looks good. And how you can see, basically is going to be 1 plus 2, and this gives us 3. It means that the first product is done correctly. Now let's create a sub vi. For this, we are going to select only this part because we are going to send it as a parameter which line we want and do the wait list. Let's go to edit, create sub vi, and that's it basically. Now to compute our signal, we are going to use from mathematics, from numeric, there is sign here. This is going to have as input our cross product that has been computed earlier. We are going to branch it, send it, and let's see if it's done correctly. It should give us 1, and it gives us 1, which means that this is done correctly. Now what we are going to need to do is basically to do this in a for function to compute this over all dataset. Now we need to compute how the weight should change based on the signum results. So for this, we are going to use yet again a function that is already implemented in LabView. That's color product. We are going to drag it here. It takes the row that is used in the same row that is used in signum function, and for that you're going to use again, you're going to get an index array. You're going to use the same index. Create our branch array, and this is going to be our first vector. And as the alpha, we're going to get the result that is from the signum. We'll let the x.py, since we won't need something else, and let's see if by default this function gives the product of it gives a.vector plus another vector. We don't have another vector, so we can leave that blank. And let's create an indicator, so we're going to see if it gives us the correct result. It should give us the same line since the signum vector is 1. And it gives us the same line, and that means that it's done correctly. Now our next step is to update the wait list. For this, we are going to use the array that we've previously computed. Now we are going to use the fact that by default the blocks that are in numeric are polymorphic, meaning that we can use also arrays. We can so we don't need to actually be variables or constants. We can use arrays, and we are going to use this polymorphic function of LabView to add two arrays, because by default what this is going to do, it will two arrays, because it will do the addition of element by element automatically, which is what we are going to need. So we are going to take the result from here. If I'm going to wait like this, and we are also will be needing the weight list that we are going to take from here. Now, to check if all of this is correct, we can put an indicator. We'll need to make this a little bit this is going to take 4 elements, and let's move it down here. And what this should do, it will basically need to make the addition between these two arrays. Let's see if all is working good. And let's see, 1 plus 1 gives 2, minus 1 plus minus 2, it's minus 3, 1 and 1. And as you can see, it's all working really good. Now let's clean our code a little bit. For that, first of all, let's move this a little bit down, so all and these two, so we'll have all in one screen. And now let's edit these names. Basically, this it will be weights. This should be more correctly. Let's call it final weight. Let's make this a little bit bigger. Now weights. Let's call it weights like this, and again a little bit bigger. Let's put a bigger font. Let's go not like this, but let's make a 24 out of this, and the style, I think it's already good enough. This is our final weights. Let's put it here. Now we won't need, and this was only for the debugging, so we won't actually need this. We also won't need these two. Let's delete wait, yes, let's delete these two nodes, these two wires. Signum, the result of Signum again, it was only for debugging purposes. That was for debugging purposes because the result is already here. Only let's say the intermediate values. This will be called initial weights, like this. Let's put this actually, let's do something like this. Let's put all the input here. Let's put this a little bit down so it will have some place like this. This is another intermediate value, so we won't need it. This is another intermediate value, so we won't need this again. Now we can delete these wires too, if I can select them. This will be our input, so let's put this here actually, and our final weights. This is our output, so it should be in another place. Let's make also this a little bit bigger. Let's make a 18. So this an 18 too. Now let's create here some text so the user will know where is our not like this. so our user will know where is our input if I can, like this. User input, so our user will know what needs to be our input. Oh, I've mistakenly made those a little bit way. Yes, like this. Size 24. Let's put this here. Now let's make this a little bit more user friendly, and for that let's see, not a container layouts. And for this, from here, let's take I think this will, oh, not like this, but layouts. First of all, a vertical split, I think it should do the trick. So, oh, not like this, no. Where it was? Decorations, this. Let's put this like this, so it should. What? Wait, I'm going a little bit up here. This is what I was searching for, because by this what we can do is to make this to be here, and let's send it to the back. Resize, reorder, move backward, move to the back. So let's put this actually here. Let's put this to here, so our user will know that. So basically what I'm doing now is to create some groups, so our user will see very clearly where is the input, where is what it's been already read, so that data set is just data, you as user you don't need to do anything to it, and where is our final result. This is why basically now I'm trying to do some decorations a little bit. Let's put this as its own here. Let's send this to back 2. Let's put this in another. Wait, now I've done something that's not quite good, because now I'm going to need to do this to select it. Let's see if I can. Yes, I could. Like this. Let's make this a little bit smaller. Let's put this a little bit down. And let's put our final result here. And to do that, let's see if I can find something that flat box. No, so let's put it in a resize frame like this. No, it's not though. But I'm trying now to find is something that will actually be more special than these two, but if not, I'm just going to change their color, I believe. Let's put something like this. This should be our results. And for this I'm going to send it to the back, and we'll get the final result. Now let's change its colors so it will no, not here, but no, we could also just let it like that. Let's add the title: Hebbian Network LabView Implementation. Let's make it a little bit bigger, a lot bigger. We could center it, and let's bold this so our user will know that this is actually the title. But Let's put it here so it will actually be behind, it will be below that line. And let's see if we can also underline it. And this should be our basically our front end. I believe it's pretty clean. Only thing that I will also want to do is to make this to a little bit smaller, so it doesn't need to actually not this one, because this is way too big for what it's doing. So let's put it like this, and this should do the trick, I guess. Let's also align this. Like this. So this will basically be our implementation of a Hebbian network using what we can also do is actually, as you could see here in this, you have compute net. Let's change actually this icon too, because when you see it, you actually need to hover it or double click on it, so you actually know what this function is. So let's add some text, and let's add here net. So when somebody comes, it will know that this is our compute net function, and not something else. Not this, but let's grab the net like this. So now it's something way cleaner to, so somebody will actually know what we are doing here. Let's save. Now what I would also add is a function to our update, because one thing that is in programming is basically that something should do only one function. And for that, what I'm proposing is basically to only make one function to do only one thing. But in this, we are computing, we are doing sign, we are also doing update, we are doing way too much things. So for that, let's do some sub-VIs here too, and for that we're going to select this part where we are basically only updating. Let's go to edit, let's go to create sub-VI, and now let's also I don't want this one here. Can I select only okay, I need to do like this. And now let's add some text. Let's call this update. Let's put this not like that. If I could select the text, actually, that would be great. The text, please. Okay, let's add this again, and maybe now it will be update. Maybe now I will be able to grab the text. The text, please. Come on. Come on. Give me the text. I don't want all of this. Wait, let's see if I can actually. It's not allowing me to grab only the text, yeah, like this. If not, I will do like this. Update. If you think that you can beat me, think again. What I've basically done here, it's well, if I can select the text and it will go to the left, I put the start of it into the right, and after I just put spaces, so I knew it will be there, my text, and I will not struggle myself again to select the text. Now it's all this is clean too. Let's see if we cannot clean some other stuff, but I think this is pretty much our oh, and I need to save this. Let's save this as update, and this should basically be our compute weight. In the next part I will go through the Python code and I will implement the Python version to see if it will give us first of all the same result, but to also see if it will basically not only give us the same result, but to see if there. Oh, and let's delete also this. I've seen it now, and let's run it to be sure there are no other. Yes, it's all good. To see if actually there are some difference regarding performance, because my hypothesis is that the Python code should run something faster, in my opinion, since Python doesn't run on Python is code, it's not visual blocks. In my opinion, it should run faster, but I'm not quite sure, especially on this data set. On this data set, I don't think it will be any difference. I hope so, because that will be kind of sad to see a difference on this data set, but who knows. Now, to make our weight persist, we're going to shift register. To do that, first of all, we need to make this node that is right here, we need to make it a shift register, not a tunnel. So we are doing this, and also after, wait a bit, let's make this a bit like this so I know that this is what I want. I'm going to also make this shift register so it will also persist in this loop, and after I'm going to make that this sum will go to this register. This wire I'm going to put it here, and this is going to be put, wait a bit, I think this is going to be put here. Oh no, just like this I believe, and I believe that this is actually, I don't actually need this. Oh nope, like this. So what we'll get now should be our, and here we're going to see our weights after one iteration. Now if we are going to put something like 10 epochs, we should see a bigger number. I guess these two are going to go really up. Never mind, I'm having a bug somewhere. Let's debug it. So it goes here. Let's go step by step actually. Yeah, step over, step into step over, because the first loop it's good. Wait, let me actually put abort. What I actually want here, let's put it I, let's put a J, so I'm going to know where both of these two are. So let's go step into the 4. This is going to be our first loop. Yes. Next iteration, y and the j going forward, though, 1, 2, okay, it goes into this, yes, okay, step over, step over, add, okay, so until now it's good. Step into the next iteration. Let's step into the next iteration. Let's go over. It's good. Until now it's all good. Oh, let's see where it's going. So there is basically one column, I guess, that's going down, but why and where? Let's see if we can find out this. So here we are having the update. So here is the update. Here we are finding the function, but somewhere we are trying. Let's go again over this. Yes, step into, step over, step into the next iteration, step into, step over. So J1 is good, J2 also good, but now it should stop. But why it ain't stopping? That's why I don't. Let's create here an indicator called n, and let's see why it's not stopping where it should. Oh, not this. Oh, single step over. Next. N is 4. Why? So basically our n is trying to go up, but why? Over. What? Into. But why is our n 4th? This should be 3. Oh, stop this. Let's delete this and put it a constant called 3. And now it all works. It does work like it's intended though. Does it? Because I'm asking, since this is a way too little number. Into, over, into. Only 2 iterations. Why? Oh, let's delete this. Why? And let's put a constant 10. Why it goes only 2 iterations? That's what I don't understand. Oh. it's not auto-indexing, so so it won't ignore what I put here. So indicator. Why it goes only 2 iterations? Let's make this somewhat bigger in this way too. Indicator. How does our size? Oh, okay, I understand this. Oh, so it takes the what I don't really takes this though. Something else. Now it works. Now it seems that I was unfortunate to not see that it was going by index and it ignored my constants that I've put here, so we should delete this, wire this up here, and now let's try to actually put it here too, because I really don't like this. This should be here, and this is disable indexing. This is what it was indexed, but now of different types. The array. Oh, now this gives us another array. Oh, I understand now. Yes. What basically happens is that our size is an array, because this is what it basically tells us what every line, how many elements each line has. So for this, what I'm going to do is to make an array index, and this takes us this, and by now I can do create a constant 0. So this it should give us the first element. Let's see if actually it's good though. Yes, and it all works great. So I should delete this. So basically let's make this like this. So basically this is our Hebbian network. Now in the next steps we will make this a little bit cleaner, so it will be easier to be read, our code, and after we are also going to implement it with Python. I've already have the Python code written, so we won't need to go over it that much. I will really talk about it. And after that we are going to put it all in a nice view, and this should be with this algorithm. Now let's go to our Python code. Data entry is a class that will basically be one row. Data set is an object that will store our data set. A Hebbian network is basically the same stuff that we already done in LabView. First we iterate for each epoch. After we iterate for each row, we compute the net, we compute the signum function, the activation function. After we get the wait list, after we go through each and we update the wait list. And here you have the compute update function. In the main, basically, because in LabView you won't call a whole script but you call only one function, what we'll do is that I've made here a test function that will basically init the same Hebbian network that I've already implemented in LabView. And first let's call here a print test, so we are going to see if all works good. And how we can see this is basically my results. So it gives us the same result, which means that both things are working quite good. Now going here, basically to implement Python code in LabView, we need to do two things. First of all, we need to open a new session to Python, and after we need to call our Python code to it. Now this is very this will be very similar to a way that you basically need, let's say, sockets or database connection, because it's basically the type of connection. And for that, let's first go to connectivity, to Python, and let's first of all create a new session. For this, let's create a new constant with our Python version. I'm using 3.9. Error in or error, basically we don't care if for errors there won't be any error. And now let's create a new Python node in which we will basically call our Python module. First of all, let's connect our session. Here we are going to put our module path. Let's create a new constant. We cannot copy the path from here because it will be in the same directory. Let's put it here, main.py. Here is the function name. Here I've called my function name test. The return time. Now, if you see, if you pay attention, I will return the wait list. So let's create a new array, a new constant array. Here I'm going to put a numeric constant. So what this will create is basically will tell our Python node that this function will return a list, because basically in LabView array is basically the list from Python. Let's move this a little bit closer. I'm going to wire up this to my, let's see, right here. And after I'm just create an indicator to see, let's put it here, Python out. Python, let's call final waits. Session out, it's again our close extension, we don't care about that too. And now, let's put this, actually, let's make this for size 4. Let's put this here, since this should be here. This was size, what size was this? 24, so let's make this 24 too. Let's move this here. Let's also move this here. Let's make actually this bigger. Oh, not this, but let's make this a little bit bigger. So what I want to now is to actually put a new text. Let's call it output. Let's make this a little bit bigger too. 24 on, oh, let's make it way bigger, 36, and let's make it bold, so it will send basically out. We can also make, let's make this smaller. Let's actually, it's obvious that it's user input. After we can make this something like this. Let's make this a little bit bigger too. Now what I want to do now is to basically modify this so it will be basically almost the same size as the, almost, I don't care to be literally the same size, but let it be almost the same size, so it will be a nice look. Now let's run it. The specified Python mode could not be imported. Python data set CSV. What? Oh, wait a bit. Wait, but it's here. Well, maybe let's see if it will work actually like this. Let's try something actually, because the data set is there basically. So what I'm thinking is that what's happening is that LabView won't run the script from where I've written it, so it won't run from this directory, but from another directory. So I won't be able to put a relative path. So what I'm going to do is try to put here an absolute path data set. This should work too, and it works. We go here, and now it works all good. And as you can see, it's the same result, which basically means that our both our Python code and our LabView are working correctly. Now in the next part I'm going to create a bit of multi-thread. We're going to do this in multi-threading because right now we do this in the same thread, and this may create some bottlenecks if the Python or the LabView version is slower, or it will create a bottleneck because it will execute one after another. So basically we don't want that. We will create some and we will run this in parallel, and it will also try to see if on this dataset, but I don't think it should, but we can ramp up our epochs and it will be fine. To see if there is actually some difference, because as I said earlier, I do expect that Python will run faster than our LabView code, simply because Python, because I believe that code that ain't written by doing visual blocks should run faster, because there is less stuff for the computers to do, and we'll see that in our next part. Yeah, so what I've basically done is I've deleted those loops because I've tried to, but I was having some strange problems with them, so I decided to just don't do parallel this time. Now to measure how much time these two functions will take, we'll basically do some test sequences, and we'll basically do a delta between the end time and the start time of the loop. To do that, we'll first add a test sequence. We'll add 2 frames, one for the base of the function and one for the start and the end of it. Here we are going to add a tick count. Here I'm going to add another. And in the end, again, like I said, numeric are polymorphic, so what I'm going to do is basically just make the difference between these two, and this should add, and here we'll see how much it took to make. I've put 100 epochs, so this should be a little bit higher. Let's put this a little bit lower, and now we'll do the same for the LabView implementation. Structures, plus sequence. Again, we don't want anything that big because it only takes a little bit of space, those tick counts. Now let's make sure that we actually select all of this, and now let's go low to this. And here now I'm going to add I think I could use this too, because we could put them in a queue. But anyway, let's add that from timing tick count. Let's add another one. I'm going to do this, it's faster. So let's put this a little bit lower. timing, tick count, like this. Let's make us now again. Thanks to polymorphism, we can do this. And now let's come on. Okay, if it doesn't want to go like that, we can always go like this. We can put wire basically like this, and we can see another indicator. First one for the LabView, one for this. Let's call them ticks. Let's also put this on the same level, I would say. Let's put it here. Let's put this to same here. Now let's see if the what 4 ticks. Why? Okay, something didn't go as we planned. Why is that? Oh, yeah. Is data set.csv. My LabView crashed earlier. So here we are going to say wait. Oh, if my English will still work. Why not found? Oh, yeah. Wait. Oh, yo, this was on singular. 2 ticks. This is curious. Now, this is actually very curious because it took 300 ticks for one. Let's see if we actually done this correctly, but yes, we've done. Because it only took 2 ticks for the other. Now, let's try and understand why it took like this much for my Python implementation and so low for LabView. Well, basically, yeah, first of all, my expectations were not met because I believed that Python will run faster. But I do believe that what it takes a lot of time is this part here, right here, to create a new session. I do believe that makes this code to run this slow. But let's one tick. Yeah, basically I do believe that this is why. Basically, I do believe that. But let's make an experiment. Why not? Let's actually how much it takes for a new session to create, because I'm actually kind of curious. Like this. Let's add now a new block because I'm actually quite curious on why it takes that much. And the only thing that I'm thinking of is that maybe to create a session with Python it takes a lot of time, but I don't understand that much why, but we're going to see now. With a constant 3.9. And let's add here a new timing. Where are you? Here. The count. One is here. Let's add another one, timing, here. Let's now make a different subtract here. What? Oh, not like that. Let's make this actually like this because it took sequence, not the actual ticks. And now let's see if this is what makes it slow. Oh, but now look, this goes up to interesting. And yeah, basically, so it takes more time. I mean, yeah, basically it's if we subtract these two, you will get basically the same time. So as you can see, both are more or less the same. Only the implementation takes more or less the same time, but what makes Python run slower when doing this type of connectivity is our session. As you can see, this takes us a lot of time. So to create this session takes a lot of ticks, and because of that makes our Python run a lot slower. It takes double time only because of this session. Oh well, I hope you enjoyed this little bit of video, and I do to the next one.